So yeah, hi everyone. My name's Andy. I'm a lecturer at the University of Loughborough. I've been there for about 3 years, and just briefly, lecturers have two kind of roles. First is teaching, and second is research. And of course, we try to bridge those two together as much as possible. So this is really about the this research side, which is used by a lot of students, but it's this new research for controlling 3D printers in a more precise way than what would normally be done with using the traditional software. So in this talk, I'm going to mostly go through a fair few examples of what sort of structures we've produced with this idea of basically telling the printer to move around in exactly the way we want, taking out the normal slicing approach. So we don't have a CAD 3D model that's sliced. We just define the toolpath of the printer directly. So I know some of you won't necessarily be familiar with GCODE and stuff. So I'm sure most of you are aware the way of normal 3D printing is you have that 3D model, and then you'll put that into some 3D printing software, which will produce GCODE. That GCODE you then load onto the printer, and that's telling the printer exactly where to move, how much material to extrude from the nozzle, and that sort of thing. So this slide's just given a very simple example of one line of GCODE, which has the command G1, which is just saying move, and then it's saying the X, Y, Z position that it wants that nozzle to move to. How fast is set by that F number, F1000, and then how much material to extrude is set by the E number. So it's really easy to type. You can manually type this in Notepad, save it as a .gcode file, and put it on your printer. But that gets pretty cumbersome for more complex processes or for more complex toolpaths. So where this all came about from is the difference between what I was thinking the ideal printing process is and what many people would think it is. So I think that in general, it's accepted that for the ideal 3D printing process, you'd have a CAD model, and then in this case, just a cylinder, and the 3D printer nozzle is in this case my water spout. And in the ideal case, it's just going to fill that CAD model perfectly with material, and we just end up with that geometry with no pores, no surface defects or anything. It's just filled with that material. And I was thinking, okay, we've got this nozzle that water's coming out. Surely there's some more interesting things we can do with that just than fill a volume. So going along this line, if you can move this around in any way, you can do much more fun things like a water pistol instead of a water cooler. And then thinking, okay, so with that freedom, what could I now produce? And the real thing, full control, is some software we've written in-house. And all that really does is it means that you have more power to do more interesting things. So instead of a water pistol, we're going for full-on flamethrowers, and it's just a way of defining that toolpath with much more detail than you could get by just typing it in Notepad. So I mentioned some of the sort of reasons why we're doing this already, but in basic terms, there's three main ones. CAD is limiting some of the structures that we can produce. So on this right-hand side of this slide, I've got an intricate tissue engineering scaffold. It's not easy to design that in CAD, even at that size. And when you start thinking about anatomical models for, say, a cranial or something, that's really difficult to get that level of geometric detail into CAD. And even more so, putting it into an STL file. So once you've got your CAD file, you then save it as this STL file, which is just another format for a 3D model. And that has really significant limitations on these sorts of structures. And in terms of the data, we'd be talking literally gigabytes of data to store the information about this sort of structure as an STL file. Whereas logically looking at that, it's simply just a few lines stacked on top of one another. So in terms of the toolpath, the G-code, it's just a few kilobytes or bytes. And then the other limitation is slicing. So this is the main one. Once you've got your CAD model and you want it to print, we did a test here where we printed some hollow cylinders with different wall thicknesses. So you can see that on the screen there. And if we take a top-down view of what the 3D printer actually printed, when the cylinder had a wall thickness that was the same as the nozzle, it was a nice, neat cylinder, or a hollow cylinder, as you can see on the left. Whereas when the wall thickness was 50% wider than the nozzle, the printer tried to kind of fill it with material, much like I was saying for the water fountain. It's not really able to think, okay, let's do it thicker wall, unless you really tell it. So for very simple structures like this, it might be possible, but not for more complicated ones. And you can see these defects on the right-hand image. They are caused by the print path because it's trying to produce, this image on the right is showing in the blue lines, it's printing a kind of circle and then printing these sections on the side as it's the slicer's interpretation. When I say slicer, I mean 3D printing software. Its interpretation of how to produce these thicknesses. Whereas this image at the top right, I'll come to later, that's on its side. That's when we've actually printed filaments with all different widths neatly stacked on top of one another. So you can achieve different thicknesses, different widths very easily. So this all came about from, at the very beginning, doing some research for very simple structures, these scaffolds that you can see on the screen. So these are used for tissue engineering. We're growing cells on them, with the idea being that this scaffold is made of a biodegradable material and it's going to eventually be absorbed or broken down, and just you'll have the tissue remaining. So it's a complicated process from that, but for 3D printing, it's very simple. It's just a grid. But you can see these blocked pores at the sides from where the polymer has kind of been oozed out of the nozzle's changing direction. And what it's doing, the nozzle's coming down to the end here, then going across, then going to the other side, then across, and then down. So it's as that nozzle is moving across, it's kind of dragging that material, over extruding at those locations. And I could see from this, there's an easy way to solve that, if you have the control, is to just, when we get to the edge, just take a tiny little step further, and then come across, then go to the other side, take that little tiny step further, and go across and back. And when we do that, we end up with all our excess polymer deposited on the outside of the structure, which we're not interested in this example. It doesn't matter. So we're taking a known limitation of the software, and with a very simple toolpath, overcoming some of the limitations. So a known limitation of the process, and very simple adjustments to the toolpath can overcome those. Another kind of application for it, when you're creating your custom G-code, is for simple structures where the toolpath, the logical toolpath, is obvious. So for this lattice structure that you can see on screen now, it's quite clear that a really neat way to print that is just for the nozzle to move all the way to one end and then all the way to the other end. Whereas if you put a 3D model of this into a slicer, it will not identify that as the toolpath, and it'll print a bit over here, a bit over here, a bit over here, and you end up with these gaps and defects. So when you take this off the print bed, it ends up being really weak, and as you stretch it, it's made of a flexible polymer. As you stretch it, it then begins to break in all these points. Whereas when we print it like this, it's really smooth and continuous, no defects, and much, much better quality. So again, very simple use of custom G-code, but achieving a really nice quality part in the end. Then going on to more advanced things, if we're defining the toolpath, then an easy way to define toolpaths is through mathematical equations. So you can see this spiral image on screen with the little block moving around it. The XYZ equation for that is just written on the left-hand side there. And T is just a number that's going to go from 0 to 1. And when it's 0, that little block is at the very bottom. And when it's 1, the block has moved all the way around up to the top. So for T set to a value of 0.5, the XYZ values would be the location on this red line halfway up. So we can program a really nice intricate toolpath. You can see on the bottom right, we've got some sinusoidal lattices. On the left, it's just a cylinder with a sinusoidal fluctuation on the widths. And you can define these really, really cleanly in the software and produce these really intricate parts. It would be really difficult to do by CAD, firstly to design, and secondly to handle that much data in CAD and slice it. Okay, so about the actual software, instead of thinking in a 3D structure, you really have to think in terms of the toolpath. So for that structure I showed you a video of earlier, the lattice, the 2D lattice, we first think, okay, I'm going to print this little section of a sine wave, as you can see on screen. Then I'm going to repeat it twice, or however many times we want. So we've defined our structure. We then tell in the software to repeat it, just like you would in CAD. You can do Cartesian repeat or polar repeat in CAD. And then I want to reflect that. So it's printing back that way. And then I want to repeat the whole lot 3 times. or twice, so we end up with it there. And finally, I'm going to move up to another layer where we just rotate this whole structure 90 degrees. So from a very simple set of commands, a very human way of describing this structure, we can get this full toolpath defined. So basically, in the software, you describe it in this human way, and then it would interpret those instructions and generate thousands or hundreds of thousands or millions of individual coordinates that the actual print path, the print and nozzle will follow. So this is a little video now which will show a few examples of this structures that were printed with this software. So instead of printing in the flat XY plane here, we're moving up and down, and we can print real size parts like this. That's the lattice you've already seen. And now these are really intricate scaffolds where we're moving the nozzle, as it's saying here, in a really fast way to draw strings. And those strings, which are normally undesired, are our actual structure. And 1/10 of the nozzle diameter is possible, so a completely different scale of geometric design. And now this is printing in full 3D. The nozzle's extruding vertically and then moving from one pillar to the next. And that movement is controlled and designed to avoid knocking those pillars over. So we can now get 3D meshes and that sort of thing. And as you saw, the sinusoidal wave structures. So yeah, lots and lots of different potential applications which I'm trying to convey here. And that's really the theme of this presentation. It's not just for one thing. I've got my ideas of what custom G-code can achieve, and I'm sure other people would have very, very different ideas for their particular application. A lot of the time, if we're talking research, this might be for say a specific material, to calibrate that material to print really neatly if you're trying to 3D print a battery or something. But it really depends, and I'm really keen to hear what other people would potentially think of doing. So this was a kind of demo product. This is what it actually looks like. And this was just a concept shoe sole, really. And I'm not a shoe sole designer or anything. So it's just to see what was possible with this kind of mathematical design. So you can see from this, and on the next slide, it's going to show some more images and a video where we've just defined, really, like I showed you on the example, just one sine wave, and then repeating it in lots of different orientations, lots of different locations, different amounts of amplitude, so whether it's a tall or short sine wave, to get this whole really intricate structure. In this case, we've got the same number of layers everywhere, but we've just changed the height of them to achieve this gradient structure. And one really nice thing about this mathematical sort of design is it's entirely parametric. If I wanted to make this 10% bigger, I just change one number. If I want, instead of, it's currently got kind of 4 unit cells going from one side to the other side. If I want to make that 6, it's just type in one number. The whole thing, the number of layers and everything. And there's a couple of points there. I mentioned there's 0 retraction and 0 travel. So this structure is yet designed so that there is never a need for the nozzle to actually stop printing and move somewhere else to begin printing, because it prints one toolpath and then it just prints a very little line down the top. And that's really good for, this is made of flexible TPU, so we really don't want to be stopping and starting with that sort of material. And those kind of intricate design considerations can be considered when you're talking about when you're creating the custom G-code. So now for visors, so the university's got a bank of Ultimaker 3D printers, and I spoke to them about doing 3D Crowd. What they were concerned with is what's ultimately happened with the National Society of 3D Printing. They were concerned as to whether there's a guarantee that these will be used. So they actually chose to go with a local manufacturing company who were working with local hospitals and care homes and produce these visors, but still with exactly the same aims and having exactly the same benefits in the end. So you can see the stack of structures that were successfully printed there on screen. And we initially printed these with a CAD file, STL, and then slicing it. And I could see immediately problems. So this, we were using nylon. You can see this amount of stringing. You can optimize to try and reduce that string, but we were also trying to optimize to print as quickly as possible and as high quality as possible. And when there's too many things to try and fix, we can reduce stringing by printing slower. But I could see it was just unnecessary. So we defined the whole toolpath for this part, and then printed it in a really quick way, because it was properly optimized for printing with 3D printers. So you can see on the right hand side there's a little screenshot showing a top down view of the sliced visor on the left, and then the one produced with custom G-code on the right. And I'm just going to blow up some of those images. So when I produced it with custom G-code, much like the shoe style, I got rid of all retraction and travel, except where it's absolutely required. So for this visor, it was required that we had a slot. They didn't want the screen to bolt onto the front. So that was just because of the customers that they were giving this to had said we want the slot. So we needed the slot with the holes in, and that meant that at some points we had to travel because it couldn't be one continuous part. But what I could easily do is say, right, where does it not matter if we travel? So when if you have any travel that's inside the slot, we would get these little blobs and stuff. No matter how well you optimized your retraction and stuff, you'd always get some blobs, and they would stop the visor going in neatly. So I said, okay, let's just put all of the travel, all of the strings in the holes. So we can easily just drill out and countersink out as a half a second operation at the end, just using a hand drill. So that's what you can see at the top there, where we've just got these 3 lines of travel on the full controlled one. Whereas on the custom, on the traditional approach, it's got some support material printed there, lots and lots of travel, unnecessary, some strange kind of tiny little bits of infill where it's doing a zigzag right in the center of the front and the rear bands. With full control, I could think, all right, what's the easiest way to print this? We make as fat filaments as we possibly can with the printer. So they were about 1 millimeter wide, ultimately from 0.4, 0.6 millimeter nozzles. So I could get away with just printing 2 or 3 bands to actually get the full structure. And then moving on to the forehead band. So this was really a critical part. There was a real problem for because this forehand bend, I don't think you can see that clearly, but it's really rough on the ones that were produced with slicing software. And it didn't matter if you told the slicing software not to travel outside the print path and stuff. Even when the nozzle followed the arc of that headband, that forehead band, to move to another section, it was over depositing, creating these bumps and vibrating up and down, and it was still a messy structure. So post-processing took ages sanding that forehead band to be nice and smooth. With this, when I designed the toolpath, I simply said, right, we can do a 1 millimeter headband with a single filament pass. So that's what it was. So there was no point did the nozzle ever leave that headband or have a seam where it started and ended, because it printed all the way from the very bottom left of the visor all the way along that headband to the very far bit, and then carried on smoothly around the corner. So there was no seams, and that really improved post-processing time. This is just showing another section, and these are all color coded according to the image on the right, by the way. Another section where we've just put that travel neatly in the gap between the parts where the hole is. And that's just showing the very, very end of the structure again, getting rid of all unnecessary travel, changing the design of the loop for the hair for the elastic band. So it's now printed vertically, which means we could stack really easily because there was never any overhangs or anything. So that's it. And then another aspect that was really cool was printing when we had to have some bridging, was just printing these sinusoidal, what do you call it, just a bridge, so that then on the next layer we could print solid material on top. So you can see on the left-hand side, that's what the sinusoid support structure looks like. And it was fully designed, you know, how much it overlapped with the existing bit and that sort of thing, so that we could get this really nice, consistent bridging with no messy bits or anything. And that's part of it. And also when we had the stack of these, the layer in between was fully designed. You know, we optimized the extrusion rate, reduced the number of lines, so defined a whole new toolpath effectively for that layer in between. What that meant was they could just be separated by hand and then a quick sand, and they were all perfect quality. So we could get really, really high throughput. So just keeping an eye on time. So then onto a few other, some of these more extreme examples, hopefully kind of disrupting 3D printing in the future. This is an example that's just about to be published on streamline slicing. So when we're designing this toolpath, we can look at something like a tensile testing specimen, which is on screen here. And on the very left-hand side, you can see the traditional approach to printing one of these specimens would be to just fill it with filaments that are of a constant width. And you could put a perimeter on to make it smoother, but you always have these seams or these gaps, when the nozzle changes direction. And people have done publications studying this and showing how that affects the mechanical properties, even when we're trying to measure mechanical properties. Whereas logically, if we just have nice streamlined filaments that start fat, then get thin, and then get fat again, then we can form this dog bone shape just by having 8 filaments all the way along, and we get rid of all those defects. And that's what you can see on the right hand side. So I'd say this would be a really nice thing that could be incorporated into slices, where the user can sort of select one face and another face, and then say, right, just I want you to blend filaments from this face to this face with no defects, no nozzle changing at all, apart from on the very ends. And then onto a couple of other examples. At the top left, you can see this lattice structure. So this one, again, fully defined. You can see on the bottom left some of my sketches that were just examples of part of the design process of that structure. So thinking, how do I want my nozzle to actually print each one of these, and making sure it prints each strut in exactly the right and same consistent way, so it always travels in the same direction from one to another. Whereas when we were trying to print this with slicers, there was always problems. Just, you know, you solve one problem and another one came, and in particular the order in which things were printed. The slicers had settings where I could nominally control that, but it would just disrupt something else. So here we can fully define and very parametric again, so we can set the exact widths, the number of unit cells and stuff, and it will instantly all update. And then on the right, we've got a structure where we're taking something that's, say, 3 times the nozzle diameter, or varying between, say, the nozzle diameter and 3 times the nozzle diameter. In this case, a micro tensile testing specimen, where we've got it fatter at the ends and narrow in the middle. And instead of the conventional approach, which would fill that with, say, 3 lines and then 2 lines and then 1 line, we just filled it with a fat material and then got thinner and then got fatter again. So it was nice, consistent, smooth printing, getting rid of all those defects. Or from an alternative point of view, offering up a way to design a perfect structure at the micro scale, as opposed to a kind of designing something that is then filled by building blocks, which would be the 3D printed filaments. And this is showing that idea in a separate application. So for printing grids, these are often printed for tissue engineering scaffolds. And typically these would just be printed with the same filament everywhere. So you have constant pore size. You can potentially vary that by varying the spacing between filaments and that sort of thing, but you can't really control it very well. That would just gradually vary the pore size. Like on the bottom left image is showing a perfectly neat grid. The second one is showing a kind of gradient, but what we're showing on the other three is, again, sort of sinusoidal changes, and we achieve those by changing the speed. So on the right, you can see how we're going fast, slow, according to a sinusoidal function, and that ends up with us having more deposition, less deposition, so we can get a really controlled design structure, which is what those two images at the bottom middle of the screen with 9 more porous sections in are achieved using this kind of process. So through custom G-code, it's just offering a completely new design opportunities that just aren't possible if you were just going to use a slicing software, which would not be able to constantly vary the film. And there is one thing, slicing software can vary the filament with variable infill for the final line, but it really doesn't do it well. And I've used that, and it's literally printed a little bit and then jumped back and printed another, and then back, and then it's just doing a really zigzaggy infill. And it is not the same as what we're doing here. It's more of just to kind of put the nozzle there and it kind of fills it. It's not a controlled gradient change of the filament width, from my experience anyway. So then on to a few more quirky ones. So I showed this is the block that was in the video with its triangular zigzag toolpath. And we've been doing tests on these where we're getting really improved mechanical properties. Some are not improving, and others are improving by a huge amount, particularly things like toughness, because it's quite easy to separate the layers sometimes if they're not bonded that well. Whereas with this, it's much more difficult because you're kind of tearing in lots of different directions. And then for intricate gyroid structures, much a similar approach. So these images you can see on screen are just this. This is a block of a gyroid as an example. And by defining the toolpath explicitly, so that every filament is directly on top of the filament beneath, aside from the offset that is required to achieve these 3D geometries, by doing that, we could really optimize the mechanical properties and get improvements over even the infill that a slicer will give you, the gyroid infill. And compared to if you had an STL model of this structure and put that in a slicer and then told it to just print it fully, we are hugely better than that, 2 to 3 times performance than that would be able to get. And this is just us playing around. If we really focused on this, we'd be able to control those properties in different directions and all that sort of thing. So then just briefly towards the end, we've used this to try and understand the strength of the interface between layers. So it's commonly known that the interface is weaker, between the layers, and you can break it in that direction much more easily than if you try to break it directly through the filaments. So we started off doing tensile testing, printing these structures vertically, as you can see on the left-hand side, and then we do a tensile test and fracture them, and then that's the pink cross-section is showing the fracture surface once these are broken. And you can see this sort of weird contact area, which is a slightly lighter color on each of the filaments, and the rest that's a slightly dark color just hasn't been in contact with the layers above at all. So it's just offering no mechanical properties from that point of view. So the whole properties are really dictated by this odd contact area, which is thinner on one side, slightly thicker on the other, a really large blobby connecting bit at the end, really uncontrolled really. So it's really hard to understand what mechanical properties are happening here. So we basically simplified it and just printed a single filament on top of itself to produce this hollow box specimen. We put in this idea of varying the filament widths to achieve the Dogbone specimen, so we can test it. If we don't do that, then when you clamp it in your machine and pull it apart, the clamps just damage your structure, even just a small amount. They have to damage it when they clamp it, and that means that it will just fail in those grips. So we need it to be wider in those grips so that it doesn't fail there. And then we did it also in the direction of the filaments. So we were basically testing the direction, if you're printing your filaments this way, testing in that direction, or if you're printing your filaments that way, also testing in this direction between the layers. And what we found was the strength is just bulk material strength. It's not weaker at all. It's just exactly the same. We've tried this for lots of different geometries. You can see many of them on screen, but even more than that. And really, the only cause, what we were finding, of weakness between the layers was because of that geometry of not having a full contact between the filaments on one layer and the filament beneath, which is quite important in terms of then thinking how can we improve the material properties. It's not about improving the bond, it's just about improving the bond area and the contact between filaments, which is a whole different problem than, say, trying to improve the bonding strength by adding some kind of acetone or something in between layers, which is the sort of thing that's sometimes been researched. So then that's it. Just a very quick final thing. Some of the other research we do is simulating these individual filaments and how their individual geometry varies. So you can see on the top right and then the bottom right for a larger structure how we're simulating at the microscale these individual filaments, and we can use that to predict what the mechanical properties will be of a structure with much more precision than if you were just to sort of use an idealized CAD model of cylinders kind of stacked together. So this is something we're also trying to integrate into slices, where we could get a preview of the mechanical properties based on the infill that's chosen and that sort of thing. So that's the end. I'm really keen to hear what people have, any thoughts people have. So please do email with any of your ideas or anything. Typically, the software is just handed out for collaborative purposes. If you're an industry that's going to try and make money out of it, then that probably we'd have to address that. And if you're just a hobbyist who's really keen to do something interesting, then again there'll be no charge for it. And lasers especially, I think there's an opportunity to define the toolpath more, not just the toolpath, varying the power or varying the speed and that sort of thing, to do much of the same kind of benefits here, but for lasers. And then this is a lot of people have been using the software. Students mostly are here to generate a lot of the images and videos used in this. So that's just my thanks to all of them. So yeah, that's the end of the talk. Need to hear if there's any questions.
Well, thanks very much, Andy. So I think you've actually answered our first question already of if the software is available. Just to expand on that a bit, is it sort of compatible with any printer, or is there sort of parameters for it to work within?
Yeah, I'll explain. It's what it basically is. You write that description of what you want your parts to be in Excel, and that will be things like if you say I want a line, and you'll say the initial XYZ coordinates, the final XYZ coordinates, how fast you want it to be printed, and how much extrusion you want, which I normally define as the width and height of a nominally rectangular extrusion. And then it will import that data and generate a line of G-code, which is formatted for a specific printer. So I've programmed the software for maybe 10 or so printers at the moment, like automakers. We've used not for Markforged, Race 3D, Prusa's and things. And basically for each new printer, I'll take some existing G-code, identify the code at the beginning of the print, which would be called the start G-code. I'll just copy that across directly. Same for the code that's at the end of the print. And then the bit in the middle, which is the actual interesting structure, will be the bit that we're really designing. So for each new printer, it takes some effort to get the format of that G-code in exactly the right language. But then once it's done, it can just generate all of these structures instantly. So yeah, it's really the user interface is just within Excel, and then the actual software, what it's doing is Visual Basic Pro, passing those instructions of the user to generate the G-code. So yeah.
Great. I'm sure expect a lot of emails from people.
That will be good.
So we've got a question from Robert. Does this cause any additional wear on the printer?
I don't know if he's talking about the Z, this in the Z direction. It may well. We haven't noticed anything when we've been printing these large structures. It sounds funny because the printers do sound different in the Z direction. We've done this for us, mostly it's Race 3D and automakers. And yeah, these have been going for weeks, printing these Zig Zag structures with no noticeable problems. I might not notice the problems because there's just so many printers, and printers just do break occasionally, but the technician hasn't raised them as causing any issues. I presume there would be an additional risk if your print bed is fairly heavy. It will also depend on the style of the printer and the print area. So some, the nozzle will move up and down, and some, the print bed will move up and down. So it will really depend, and I think it would need to be investigated specifically for that printer. But for us, we're just interested in, is this idea worth thinking about? Does it actually offer any potential benefits? And if we can prove that, then we look at whether it can be done really in a industrial setting or using 3D printers that people have, or design new 3D printers that are perfectly happy to move in X, Y, and Z all at the same time.
Great. So we've got another question from Len. Do you think this research could make its way into other print software?
Yeah, for sure. So this, as an example, this gyroid type structure, which we've designed, it's extremely simple from the mathematical description. So that could just directly go into Cura. And I have spoken to the Cura people at one of the conferences, and they're quite interested in all this sort of thing. So I haven't approached them with these results because they're not published yet. But that would just go in as another option. They've currently got gyroid, so they could have Andy Gleedle's gyroid as well, whatever we call it. And that will be then immediate benefits for the end users. In terms of designing the structures, designing the G-code, I don't see it fitting into slicing software because it's completely different. You don't have that CAD file. The settings that you normally choose for slicing just don't apply. So I'd probably see you developing the research side or the product development side with CAD side of software. So this is like CAD for G-code, and then producing some slicing software that would integrate those understandings into a specific slicing software for a particular type of part. So I could have this type of structure might be suitable for all horseshoe type objects, and it would just adapt for all horseshoe type objects, but it wouldn't work for somebody that's trying to 3D print a vase or something. So that's the kind of way. But yeah, putting it into slicing software would be really difficult just because it's a completely different way of thinking. The obvious thing would be to put it into CAD software, with the slight problem that CAD is so focused on geometry that it really isn't optimized for those other aspects which are really critically important, like temperature and extrusion rate in particular, and that sort of thing, and speed. Every single line you might want to define the speed of.
Great. I think that takes us really nicely into our next question. It's from Leo. How do we customize the toolpath like you did for the face shield?
So it's not customized, it's fully designed. It is literally like if you've got a house, you're designing a house and you're designing the walls, you can't think, oh, I'm going to use 2.5 bricks. You've got to work with having either 1 row of bricks or 2 rows and space in between, or even more like a log cabin. If you're designing a log cabin, you have to design every single log. It's part of the design process. So for modifying, I can't remember what the exact word was, but it can't really optimize or modify an existing toolpath. You would have to look at every single layer of your part, or even better, look at the geometry. What is it trying to achieve? And then define a toolpath for every single layer that will actually do that. So for our visors, it was extremely simple. I was thinking, okay, I'm going to have 2 lines printing this top band, 1 over here and then 1 back. So I'm back at my starting point. I'm then going to use 3 on this internal band and 1 for the forehead band, which means I can do 1 across, 1 back, and then the 3rd one across, and then the forehead band back. So I get to my starting point, and then I can just say, right, repeat this for however many layers I want. It's really the whole design of your structure has got to be at the scale of those individual filaments. So you have to know exactly where you want them to be. So you don't, for this arc, that might be made up of, say, 360 filaments or something, each little segments. You don't need to define that, but you do need to define the center point of the arc, the fact that you want it to go from this angle all the way to that angle, and that kind of detail. And then that's why it's full control to kind of take that simple information and produce all the tiny little XY coordinates for the G-code. But yeah, it has to be thinking at the actual individual filaments position and size and location.